In the previous section, we have learned how to find a chemical formula of a compound with questions like this. However, even we understand the chemical formula, it doesn't mean we can understand the structure of the molecule. For example, we are given flour and egg and sugar. Does it mean we can make a bread for sure? Or we can make something more interesting? Similarly, with the following atoms, C3HAO, we can build different molecules, and the most important point is they have totally different physical and chemical properties. With more and more atoms involved, we can expect the situation will just become more complicated. With 4 to 5 carbon atoms, the choice of structure is limited, but there are more than 300 possible structures for the combination of 20 carbon atoms, and there are many possible structures for the combination of 40 carbon atoms. Now, you can understand why the chemical formula alone cannot show the molecular structure. All these possible structures are called isomers, which are different compounds with same chemical formula. Different isomers can be classified into two categories: structural isomer, which the atoms are bonded in different order, or stereoisomer. In this example, the P and B represent the same components but with different orientation. And we will discuss the structural isomer first. The structural isomer can be further divided into three categories. The first one is chain isomer, where different molecules have same functional group but different length in carbon chains. Consider these two molecules. Both molecules have 4 carbon atoms and 10 hydrogen atoms, but the longest carbon chain, or we call carbon skeleton, is different. Butane got 4 atoms, while methylpropane got 3. That's why two molecules have different names. Next, structural isomer is called position isomer. Again, they have same functional group, but attached to different position in the carbon skeleton. Earring and nose ring are good illustration for this. A typical example is propane 1O and propane 2O. Both molecules have same length in carbon skeleton. The difference in position of OH group make these two molecules have different chemical properties, which will be discussed later. Again, these two molecules have different names. The last structural isomer is functional group isomer, where the molecules belongs to different homologous series. Here shows the left one is aldehyde, ended with Al, while the right one is ketone, ended with ONE. Another example is the left one is alcohol or alkanol, while we have no idea what the right one is. Actually, this is called ether, which is not included in the DSE. Finally, here shows the flowchart for distinguishing different structural isomers. First, are the molecule have same chemical formula? If no, then they are not isomer at all. Next, are they have same functional groups? If no, then they are functional group isomers. Are they have same length in carbon skeleton? If no, they are chain isomers. Finally, is the functional group attached to the same position in the carbon skeleton? If no, then they are position isomer. If yes, then these two molecules are not structural isomer at all, or they are just identical molecules.